Welcome to our next lecture in this series on condensed matter theory. In this lecture and the following lectures I want to talk about the Sommerfeld model. And the Sommerfeld model is basically an extension of the Drude model, including quantum mechanics. In 1900, Drude introduced his model, which of course was well before the quantum mechanics as we know it today. It was shortly after the discovery of the electron, and it was in the time when Planck was writing up his ideas on black body radiation, which of course sparked a lot of research on quantum mechanics, especially the Heisenberg mechanics. But the real breakthrough came in 1926 when Schrödinger published the equations that we now know as the basic of quantum mechanics. Actually, in the same year, Schrödinger published early in 1926, Dirac lately in 26. Dirac published an important paper on quantum mechanics, not the paper where he is really known for, but he made an extension of the Schrödinger equations to many electrons, and thereby basically introducing Fermi-Dirac statistics. And this is what Sommerfeld used, and in 1928 Sommerfeld introduced his model. And the addition of quantum mechanics to the Drude model solves a few problems. We didn't discuss thermoelectrics in the Drude model. We'll talk about this in the Sommerfeld model, which now starts to work and get quantitative correct results. And we'll also find that we can explain the specific heat of metals in the Sommerfeld model. So what is the Sommerfeld model? And as we work in quantum mechanics, we can basically start from a Hamiltonian and work from there, which is slightly different than the paper that Sommerfeld introduced. Actually, the paper of Dirac, which I list in the literature, is really nice to read. The paper of Sommerfeld, well, you can read it, but I do not really recommend it. So the Hamiltonian that Sommerfeld used basically included the kinetic energy of the electrons, but nothing else. So just like the Drude model, we neglect all interactions between the electrons and all interactions between the electrons and the nuclei, so all Coulomb interactions. We'll introduce some scattering at some point that the electrons have, but we do not give a microscopic model for this scattering. We'll do this later in the lecture when we talk about disorder. But for that we have to have Green's functions and Dyson equations and diagrammatic expansions to be able to discuss this. We can also write the Hamiltonian in second quantization, and our prefactor h bar squared k squared over 2m. And then we can create and annihilate an electron with the same wave vector, momentum. Notice that I often talk about momentum when we write down wave vectors. Of course, there's a vector h bar in between, but we very often neglect that, and then of course wave vectors and momenta become the same. So in units where h bar would be would be 1, they would be the same. The nice thing of this Hamiltonian is that it is diagonal in momentum, and therefore we can immediately write down what the eigenstates are. And the eigenstates are our basis functions, and these are of course the eigenstates for one electron. Our one electron eigenstates are functions of the coordinate r. They have a quantum number k, your wave vector, and they are proportional to e to the I k dot r. In order to represent physical states, our wave functions need to be normalized, and a plane wave is not normalizable. the integral over the norm of a plane wave is the constant over entire space diverges. In order to normalize this, we can place the particle in a box. And we use a box with length L in all 3 dimensions. And L is very large. And we let L go to infinite. In the end. So we have a volume which is L cubed. And when I have a box with periodic boundary conditions, not all wave vectors are allowed. We get a quantization of our wave vectors. So our wave vectors that are allowed are restricted to 2 pi over L times an integer, such that the wave repeats with the length L. And with that, we can now write down a normalized form of our wave function, square root 1 over v, e to the I k dot r, and k is 2 pi over L, and 1, and 2, and 3, and ni is a real number, an integer number. And with that we have an orthonormal basis for our states, and those are the eigenstates of the one-particle Hamiltonian. Now we do not want only one-particle eigenstates, we are interested in many electron eigenstates. And not only the eigenstates, but in principle many particle states. Well, we can make many particle states by putting electrons into the one-particle eigenstates. The one-particle eigenstates form a complete basis set, so we can look at all possible ways to put n electrons in these one-particle states, and that then forms the many electron basis set. As our Hamiltonian doesn't include any interactions between the electrons, when we put electrons into the one-particle eigenstates, that also gives you an n-particle eigenstate that is or an n-particle state that is an eigenfunction of the Hamiltonian. So we can define di as a set of n different states, one electron states, and states are labeled by a k vector and a spin. And then my many electron state is given by the creation of all the electrons or all states, all one-particle states that belong to the set di a dagger tau 0. And then depending on what I is, you can pick different combinations of states. And that then gives you your many electron bases. And as discussed before, the number of many electron states that you can generate in this way is enormous. If we want to look at the n-particle ground state, then we can easily do this, as the energy of our states is just the sum of the energy of the single particle states. We can generate the ground state by taking the states with the lowest energy. So we take the states with the smallest wave vectors. So we define some wave vector, and all states with wave vector smaller than that wave vector are occupied. All states with a wave vector larger than that wave vector are empty, and we of course have to fill both spin up and spin down electrons. So that will be our ground state. Now you would normally say for a certain volume I want to generate n electrons, so a a cubic centimeter, you want to generate about 10 to the 23 electrons. And here I'm not telling you what n is, but I say, well, we pick a wave vector and we fill all states with a wave vector smaller than that wave vector. Well, of course, we can change the size of kf until you find a state that has the correct number of particles. But one of the questions that we need to answer is what is for n particles, what is the Fermi wave vector, which is the wave vector that we call that is separating occupied and unoccupied states. This question we will address in the next video, and actually in the next videos I'll have a few short videos on the different properties that we have for such n-particle states, like band structure, Fermi, surface and densities of states. For a free electron model, these are relatively simple, but these concepts will come back when we go to crystals, have additional potentials, and then they will become more involved. But the concepts are already there and we can lay them out here. Well, thank you for your attention. We see each other in the next video. Stay healthy.